it's been a long time. What did we cover so far in chapter 2? We talked about average rate of change. Say over an interval AB. What was that? Average rate of change of a function f over some interval. You hear about that. We spoke about instantaneous rate of change. And what was that? Right, that's one form. It's also equal to the limit as x approaches a. X respectively a of the average rate of change, right? So the average rate of change gave you the change over some interval, and you basically take a limit to close the interval, and you get it at an instant. This guy, what did we call it? Derivative. It's equal to the slope of the graph at the points of x. Or it's called the instantaneous rate of change. Okay. So that's what we covered. We did some examples. Using the definition, but we also looked at what's called the power rule for derivatives. Which basically says to differentiate anything that looks like x to the n, you get what?
N minus 1.
So that was a very important rule. I proved it for positive integers. The proof in general we need logarithms for, so I can't really prove it because we don't do logarithms in this class. And we did some examples doing that. And I skipped some stuff in 2.2 that I want to go back to right now, and then we'll continue the power rule onwards. Okay, so that's where we're going to pick up. So we introduced the derivative, very important component in calculus 1. Most of our time is going to be spent worrying about the derivative, right? But it's just the instantaneous rate of change at a point, which gives you the slope of the graph at the point. In particular, the slope of the tangent line. Right? So it's very important that you understand that these are all synonyms, they're interchangeable. They all mean the same thing. Okay, so it turns out the derivative does not always exist, right? So I know this formula looks, we've done tons of cases where we've plugged in functions into this, and yeah, we can simplify it, but it turns out that you can't actually always do that. It's a limit, and it's possible for limits to not exist. So what I want to talk about first before moving on is some of the cases where it will not exist, and what that means. So probably the most important case is the following. So differentiable means this limit actually exists, this limit that we're talking about here, right? So once that exists, we call the function differentiable, right? F is differentiable on an interval if it is differentiable at all points in the interval. Okay, so this is what it means to be differentiable. It means that we can actually find that limit. A lot of times we actually have a nice formula for it. But as long as we can find this limit, we say it's differentiable at a certain point. And that definition of differentiability is good enough for a Calc 1 student. If you're a math major, you go higher, it's going to be a little more involved. And here's an important theorem. If f is differentiable at A, then it is continuous. Right? Differentiability implies continuity. This also means the derivative does not exist where a function is not continuous. So if you're not continuous, this is a case where you cannot find the derivative.
Wait, I have a question. I don't really get what differential is. So is it the same as
Differential just means we can find the derivative, right? Which means we can do this limit and we'll get an answer,
Oh,
right? So remember, it's a limit just like any other limit, right? So D and B is always a possibility, right? There might be a case where it just does not exist. But as long as it exists, we can find an answer. It means we can find the derivative. We say it's differentiable, right? And there are cases when the limit will not exist, and I'm specifying the cases now. One such case when it will not exist is if it's discontinuous, right? Which means if you have a hole or a jump or an asymptote, you can't actually find a derivative. It's not differentiable at cusps. Basically sharp corners. If your graph has a sharp corner, you can't find the derivative there. I'm going to give you examples of this. So there are three cases where we actually can't find a derivative: if your function is discontinuous, if it has a sharp corner, or if the tangent line is vertical. So, example, these functions example. Here's A, this is your function, has a gap. Here's A, this is your function, jump. Can't find derivative at point at A. Or if you have something like an asymptote at A, can't find derivative here. If your graph does something like sharp corner, can't find the derivative also. Your function does end up vertical at any point, like here. You draw a tangent line to the curve, you get a vertical line. You can't find a derivative, right? The limit will not exist in these cases. Right? You can tell from the pictures. But to just give you a concrete example.
Professor,
Yes.
can you explain for the middle?
This one?
Yeah.
This is an asymptote. Right? There's an asymptote, a vertical asymptote at A, right? Which means it's discontinuous.
Okay.
Right? Now remember, you want to take the limit as you're approaching this point, right? But the function doesn't exist at the point, which means f of x plus h doesn't exist, f of x doesn't exist, it doesn't exist at this point, right? That's the easy way to think about it. The most common type of example here is y equals absolute value x at x equals 0. Right? This graph here, remember it has a sharp corner at the origin. Right? Turns out you actually cannot differentiate it at the origin. If you're not at the origin, everything's okay, but at the origin you can't. And say, how do you know? Well, remember, f prime was a notation for derivative, right? So f prime of 0 would look like what? What's the limit as h approaches 0 of f of 0 plus h minus f of 0 over h, right? Now, if your function happens to be the absolute value, this would just be the absolute value of h minus 0 all over h. Right? But what is that limit?
What's the negative? The both?
Does not exist, right? Because if you're approaching, we did examples like this. So you're approaching 0 from the positive side, the absolute value just gives you h, you get 1. If you're approaching for 0 from the negative side, absolute value gives you negative h, you get negative 1. Right? It doesn't connect, right? So this limit actually doesn't exist. So at this sharp corner, this limit does not exist, which means it has no derivative there.
Well, Professor, how did you end up with the absolute value of h?
My function is absolute value of x. Right? I'm doing f of 0 plus h, which is absolute value of 0 plus h.
Also, it was the absolute from the beginning.
Yeah, I'm doing this function into the example. Right? Absolute value of x at x equals 0 is not differentiable. Intuitively,
why the function is not different, why there is a vertical value?
Because what's the slope of a vertical line?
0.
Slope of a horizontal line is 0. What's the slope of a vertical line? Right? Vertical line has no slope, right? Slope is infinity. Right? A vertical line has infinite rise over no run. So at the end of the day, intuitively what this means is you can find the derivative whenever your function is smooth. And they actually define that with more rigor later on, but we don't need it now. Basically, smooth just means it's points where you can draw a non-vertical tangent line, which means your function is approximately linear there, which means it sort of looks like a straight line if you zoom in, right? So if you have this random function and you want to figure out, can I find a derivative here? Well, zoom in there, right? If you zoom in far enough, if it looks like a straight line, then yes, you can find a derivative, right? Right? It means that tangent line would be very close to that, so when you zoom in enough, they'll look like one and the same thing, right? At sharp corners, if you look in the case of a sharp corner, right? If you zoom in far enough, it will never look like a straight line, right? And at the same time, what that means is you actually can't draw a tangent line to that, right? Because how many tangent lines can you draw here? Well, that's a tangent line, only touch at one point. That's also a tangent line. That's also a tangent line. That's a tangent line. That's a tangent line, right? There is no one tangent line. It's undefined. What is the tangent line? It could be whatever. Right? Almost any line could be a tangent line, right? So, can differentiate here. Right? You can't draw a tangent line because if you zoom in far enough, it doesn't look like a straight line. Right? And of course, forget it, the function is not continuous, you definitely can't draw a tangent line here. Right? Because the point doesn't even exist for you to draw it through. So I wanted to mention that. I mean, we're going to get to more computational stuff, but for now we're just talking about, intuitively what this all means. And knowing the intuition behind the derivative is going to help you a lot with the word problems that you're going to encounter. So I thought it was good that we covered notes. Something else you'll need to know, we can take several derivatives sometimes. That means if you take a derivative and you get an answer, a lot of times you can take a derivative again. And then you can probably take a derivative again, and take a derivative again, right? In Calc 3, you really learn about functions where you can take derivatives a certain number of times, but just know that it's possible to take a second derivative, a third derivative, a fourth derivative. So, example, y equals x cubed. Remember notation? If I say derivative here, again, it's a premature example. Derivative, it would be what? 3x squared. If I apply the first rule, It turns out that if I look at this as if it were the original function, I could do a derivative again, right? So what we can do is we can put 2 primes to say I'm doing a second derivative, right? And then I can get 6x. Right? We're going to talk about derivatives here. And hey, that's another function. Can I take a derivative? Sure. You can find a third derivative. Put 3 primes, right? That will just be 6. Could we take a 4th derivative? Right. Eventually, writing primes just gets retarded. The notation is you open a bracket and you put it in a power, right? Whenever you see a power in a bracket, it means derivative, right? It doesn't mean the actual power. So this would mean the 4th derivative. And so what would that be in this case? 0, right? Because that function is just a horizontal line. The slope of the tangent line is 0, right? So in other words, notation. Y to the n or f to the n. And it's very important that you put it in brackets. Means the nth derivative. Otherwise, remember the Leibniz notation, dy dx? Right? This just means the derivative of y. It turns out that, so this is the first derivative. It turns out if I take a second derivative, what I can do is I can take derivative with respect to x of the first derivative that I took. And so I can write this notation as d squared y dx squared, and etc. I can write dny dx to the n for the nth derivative.
Wait, why didn't you multiply dy over dx by dy over dx? Why didn't you just say d over dx?
Let me talk about how the notation works a bit. Maybe that will clear up some confusion. Dy dx means the derivative of y with respect to x, right? So basically, you say d dx of y, right? This guy tells you the function you're differentiating. This guy here tells you what the input variable is. So I'm calling the function y, the inside variable is x, right? So So d dx means differentiate whatever you see here, right? So when I put d dx of dy dx, what I'm saying is differentiate this function, right? So d dx just means differentiate whatever is to the right, right? If I put dy dx, it means I'm taking the derivative of y and then I'm just multiplying by another derivative of y, right? It's just multiplying 2 first derivatives, but that's not what I want. I want to differentiate this guy. Right? Whatever function I want to differentiate, I put it beside the dy dx. sort of how the notation works. I think that's all we wanted to cover from 2.2. 2.3 is a lot more fun. That's the more computational part. Basic rules. We already did the power rule for derivatives. This was you differentiate x to the n, you get n x to the n minus 1. We also did sine. Derivative of sine was what? The sine. Maybe I should write that stuff. What's the power rule? So did some trig derivatives. We're going to cover the other ones as well. The derivative of sine is cosine x. The derivative of cosine x is minus sine x. Yes, you should have these memorized, and you're going to have to memorize a whole lot more, but for now, that's that. How about constants? What's the derivative of a constant? The derivative of a constant equals 0. Why? Well, intuitively, because a constant is just a horizontal line, the tangent line is 0. But you could also, if I take f of x to be a constant, then f of x plus h is also a constant, right? Because there's no x to plug in. And so if I take f prime of x, that's just the limit as h approaches 0 of f of x plus h minus f of x all over h. It's just going to be 0. You're a constant. You just get 0. Always be 0. So it doesn't matter what the constant is. You will always get 0 if you take the derivative. For example, derivative of 1. 0. Derivative of pi is 0. Derivative of 17.954 is 0. Doesn't matter the constant, you will always get 0 to take the derivative. Right, so this is a rule that you should know, constants. Sort of know it by heart. They mentioned this in the book, I don't know why, because it's sort of a consequence of the power rule. But they also mentioned the derivative of x is 1. And use power rule. With n equals 1. Or note if f of x equals x, then the limit as h approaches 0 of f of x plus h minus f of x all over h. So that's just going to be the limit as h approaches 0, x plus h minus x over h, which is clear. Right? So the limits will always be consistent with the rules that we apply. Another rule, constant factor rule. I mean, we've been using these the whole time, but I just thought I should mention for anyone who hasn't been catching on. If you take the derivative of a constant times a function, that is just equal to the constant times the derivative of the function. In other words, if you have a constant in front of a function, ignore the constant, differentiate the function, and just leave the constant attached to it. That's it. So, why? Again, you can think in terms of limits. This would mean that if you have c times f of x plus h minus c times f of x, right? Just replace the function with a constant times the function. It's a limit. We know we can factor constants outside limits. We proved that earlier. So that's just c times f prime. All right, so if you attach a constant to your function, you can factor it out. It's no problem. So, example, if you want the derivative of 5x to the fourth. We can just think of this as 5 times the derivative of x to the fourth, which is just 5 times by the power rule, 4x cubed, which is just 20x cubed. We've been doing that when we did the 3x squared and then we got the 6x in there. That's the rule I was applying. So the constant factor rule. What other rule? I already proved the sine and cosine. Is there any other rule that I would mention? Well, I gave some more examples here. Do you need more examples? No. Yeah.
So in here you don't need to get the derivative of the function of the constant at all?
No. If there's a constant multiplying, just leave the constant where it is, differentiate the function, and just multiply.
If it's like 5 sin x, you do the sin x.
It's the same thing, right? So if you have the derivative of 5 sine x, it's just the same as 5 times the derivative of sine x, which is 5 cosine x. Right? And typically you won't be expected to write this. You just know that, oh yeah, right? They don't expect you to write this. But just know that behind the scenes, that's what's happening. You're factoring the constant out, differentiating the function. Yeah?
So in, like, if you want us to differentiate a fraction, would you want us to do it individually or do the whole thing with whole? So like a compound fraction, like 20x cubed over 30x squared, something like that. Would you want us to do it individually and then divide it?
No. There's something called the quotient rule that will deal with that. That one in particular is just simple. You can cancel the x. Do the power rule. But yeah, with divisions, we're getting to that. That's actually the next section. There's a whole rule you have to go through.
So like chain quotient?
Yeah. There's things called the product rule, the quotient rule, the chain rule. We're going to deal with situations like that. For now, we're just covering the basics. There's something called the sum difference rule. Basically says if you want to differentiate a sum or a difference, right? So I'm differentiating f of x plus or minus another function, g of x. You can just differentiate each part and stick it together. Derivatives distributed across sums. So, for example, if I ask you to differentiate 5x cubed plus 3x plus 1, right? Here's a sum of functions. Let me do 2 first so you can see the rule. Here's two things being added. If you want to differentiate a sum, all you do is you differentiate each part. So you differentiate the 5x cubed, plus you differentiate the 3x separately. Right? The power rule here says you get 15x squared. Right? Because you leave the 5 alone, differentiate x cubed, you get 3x squared, then multiply by 5. And if you differentiate this, you just get 3. Because the derivative of x is 1. Differentiate each part.
Don't you have to like, where's the part where you have to like get the derivative again? Because can't you get the derivative of 5 at 15x squared again?
Come again? 15. Well, I didn't ask. I just asked for the first derivative. Right? This says differentiate that only one time. Right?
So when do we like get multiple?
One, if you're asked for it, and two, if you're doing a certain function. There are cases where we'll use multiple derivatives. You'll know when they come. I'll let you know. Now covering the basic rules, any other basic ones? And again, this is because derivatives are limits, right? If you take the limit of a sum of things, you can break up the limit along the sum. We did that earlier with limits. Just trying to do some problems. Getting bored with the basic ones. We started using them the whole time. So I want you to find all the points where the tangent line is horizontal to the curve y equals dx cubed minus x squared over 2 minus x plus 7. And the third derivative. Let's actually go through these starting from the left. How do we find the derivative? So remember notation, I can write y prime, or I could write if I want dy dx, they mean the same thing. Okay. So y prime in this case would be 6x. Right, because you leave the 5 alone, the derivative of cosine x is minus sine x, so it just becomes minus 5 sine x. Okay, what about this one?
You first change the radicals and the denominators. You bring it up.
Okay, how do we change that?
So 2x to the power of 1
2x to the half,
Times 2 is 1.
plus 1x negative 3
x to the minus 3,
minus 2 sine.
minus 2 sine x. Right. So some people are trying 1 over 2 radicals, so how do you get it? So the first rule was use the rules that you have so far, right? You don't have a rule with radical, you don't have a rule with division. You have to rewrite it so it looks like a rule that you have, right? A lot of calculus is that. Rewriting stuff so you can apply some rule and then do stuff. So in this case, you have to rewrite it so it looks like x to the n, right? Or sine x. Now, if I take the derivative, what does it say?
Just
Bring down the half, and just subtract 1 to get minus half, right? It says bring down the minus 3, subtract 1, so I get minus 4. Your sine is cosine. So here the 2's cancel. So that's just x to the minus a half. I can write that as 1 over radical x minus 3 over x to the 4th minus 2 cosine x.
Wait.
Questions?
I don't get how in the third part you did x to the negative 1 half.
Oh, I'm using the power limit. Right, I know that the derivative of x to the n is n x to the n minus 1. Right? So it means that the derivative of x to the 1 half is 1 half x to the 1 half minus 1. Right? A half minus 1 is minus a half. So you're just applying the. Any other questions on this? How do you figure out where the tangent line is horizontal? I probably need more space than this.
0. So the 0.
What?
You said derivative of y equals to 0.
Alright, so probably need more space. Horizontal tangent means slope is 0, means derivative is 0. So that's what I'm going to do. Find the derivative set equals to 0, I can find where the tangent is horizontal. Right? Y prime is equal to, what's y prime? Minus x. How do you know that's minus x? You did the quotient. Do you agree?
2x over 2.
2x over 2, right? You wouldn't do the quotient for that. When we get to the quotient, I'm going to talk about situations where it's a bad idea to use
just
the quotient.
x
Uh,
minus 1.
Can I get rid of it?
There you go.
Besides, I thought the quotient would get at least sort of unfair. If you see x squared, you see something like y equals x squared over 2. You sort of think of that as a half times x squared, right? And then you use a constant factor. Right? So that just means you get a half. The derivative would be a half times 2x, which this would cancel this being x. Right? You wouldn't do the quotient. It's actually too much work. Right? Usually if your denominator or the numerator is just a single term, especially if it's a constant, you don't do the quotient. But we'll talk about it. So So yeah, this would just be minus x, this would be minus 1. Right? And so I want to figure out where this is 0. This implies I need 6x squared minus x minus 1 equals 0. Can I solve that? Is that factor?
Yeah.
3 and 2 maybe, if I make a minus 3 and a plus 1. Alright, so yeah, so then x equals minus a third, or x equals a half. Right? And if you want to find the points, you plug in here and find the corresponding y values. That's not that makes sense. Right? So that would be where the tangent line is horizontal. Okay. Horizontal tangent line means slope is 0. Find derivative set equals 0. Find the third derivative. So you start by, of course, finding the first derivative, which is
Negative sign.
derivative sign is cosine. Then you're going to find the second derivative, minus sign. Then you're going to find the third derivative, negative cosine. Right? Derivative of sine is just positive cosine, so the negative sign stays. Go on this one. Okay, start with the first one. First derivative, minus 3 sine plus 2 cosine. Okay. Second derivative, minus 3 cosine minus 2 sine. Third derivative, 3 sine minus 2 cosine. Third derivative of this one. Start with the first derivative. You get what? 3x squared plus 4. Second derivative, 6x. Derivative a constant is 0. Third derivative, 6. What about this one? That goes to 0. Second derivative, third derivative. Okay, this one. Derivative is 10x plus 2. Second derivative, 10. Third derivative is 0. Can you come up with a rule with the number of derivatives and the degree of a polynomial?
I have a question. It tells you to find the derivative of 0, or if it was like the fourth derivative of the last
Sure,
one.
I can find the fourth derivative. What would it be? Be 0, because 0 is a constant. Right, so you can keep finding derivative of 0, you'll always get 0.
No, I thought you had to
0 is a constant, so the derivative of constant is 0. Right? One thing to notice about polynomials is that the derivative always breaks down to degree, 1 by 1. Right? So if you're taking more derivatives than you have degrees, you'll always end up 0. So when you saw this, you saw the degree was 2 and asked you for 3 derivatives, you could have just jumped and said this is 0. And you wouldn't have to show any more because I'll assume you know what I'm saying. Right? If you have more than 3, then you have to do it. Okay. Another application of multiple derivatives, since someone was asking me. There are physics applications to multiple derivatives, one of many. We'll see more applications, but one application, multiple derivatives. By the way, you might hear this called higher derivatives. Distance, velocity, acceleration. So it turns out that if I let S of t be a function that gives me my position at time t. So I write a function of time, and I call this my position function. It turns out that the velocity of this function, if I take the derivative of that, right, it will give me the velocity of the object that I'm considering. And if I take the derivative of the velocity, which is in fact the second derivative of position, that gives me acceleration. And you can think about, what speed actually is. It's distance per unit time, right? It's rate of change of distance over time. So to actually move down between these three, you differentiate. By the end of the semester, we're going to learn how to go backwards. And it's called anti-differentiate, but that's not for now.
Wait, can you explain that again?
Huh?
It's kind of
These are just, if you have something that gives you a position function, like this function tells you where something is at any given time.
So the derivative of s.
If you take the derivative of position, you get velocity. It tells you how fast the thing is moving. If you take the derivative of velocity, you get acceleration. It tells you how fast its speed is changing. Right?
Or the second.
Derivative always tells you how fast something is changing. Right? Speed tells you how fast your position is changing. Right? Acceleration tells you how fast your speed is changing.
So you can either find the first derivative of velocity or find the second derivative of the position.
And that gives you acceleration.
So
Turns out, what?
Is that S something you just made up? S of t?
These are the typical letters.
Oh.
It's what they always use, SV and E. I don't know why. Anyone knows what that is called? Jerk. It's called a jerk. Right. So, for mathematics it calls you a third derivative, which I have seen people get called. Yeah, you mostly see that in physics, right? So the third derivative of position is called the jerk. We're not going to use it, I just thought that was nice.
How's it called?
I don't know what it's called. Third derivative is called the jerk, yes. Let's do an example of this.
Is that going to be a test?
Of course.
What is third?
The first test is not completed. No. Completed how? At time t equals 0. Divergence. That is 32 feet. So, do physics class, this is in chapter 1, it's free fall. his position above the water is given by this function. S of t equals minus 16 t squared plus 32 t plus 32. T is time in seconds. Right, so that's the situation. Someone's on a platform, they dive off into a pool. You can map their position by this, which is a typical position for, it's a typical equation for free fall on Earth. Here are the questions. When will the diver hit the water?
I'm sorry to interrupt. What time is your class over?
In 15 minutes.
They assigned to me this room after 6 o'clock, so I wanted to make sure because it's our first night here.
Oh, we go to 6:15 on Tuesdays and Thursdays.
Yes?
We have 6:15 on Tuesdays and Thursdays, so we
Okay,
should
I'll let them
be.
know. Don't worry. I'll let them know. Okay? It's just that we have problems with our room and they assigned us this week. So they probably don't know. So I'll let them know. Okay? Thank you very much. So 6:15?
Yeah.
Thank you.
Like, well, I guess we have to go, Joanne. I want to stay, but you know. Okay. Lots of questions. That's actually the last example for this section. Okay, a diver jumps from a platform, is 32 feet above the pool. His position above the water is given by that, where t is time in seconds. When does the diver hit the water? Alright, he hits water when height is 0. This means I just need to set S of t equals minus 16t squared plus 32t plus 32 equals 0. Which means I can divide by minus 16. And can I actually solve that? What's the number? I'm sure I wrote down some of that fact. So what's the 16? It's not 32. This is, I mean, this 16. Once you don't want to use the quadratic formula. Okay, so that should factor. So now we have the minus plus. So t is actually 2, or t is minus 1. We reject because we're considering negative time to be nonsense. So he hits the water after 2 seconds. It'll be in the air for a total of 2 seconds. B, what is the velocity? Remember, the velocity function is just the derivative of the position function. So this is just going to be minus 32t plus 32. Plus 16. Yeah, we got plus 16. This is velocity at time t. What's the velocity after 1 second? This is feet per second. I'm not going to care too much about units in this class, but in physics class, units are super important. Yeah. What does it mean for velocity to be negative 16? Down, right? In this case, velocity gives 2 directions. If it's positive, it means he's traveling upwards. If it's negative, he's traveling downwards. So after 1 second, he's already on his way down. What is the diver's impact velocity? When does impact occur? When t equals 2. This means impact velocity is just the velocity after 2 seconds. Huh? 48.
Yeah, I think no, that's 2 seconds.
We found it in part B.
Oh, yeah.
Part A, right? We know when he hits the water, right? That was after 2 seconds. So now I'm asking what is the velocity when he hits the water. So I put in 2 seconds. What about, what's his acceleration after time t? Acceleration would just be the derivative of the velocity, which is, I take derivative of minus 32t, that's just minus 32 and derivative. So this is feet per second squared. And that's it. Okay. When is the diver traveling upwards? When is he traveling downwards? Remember what we said, upwards mean velocity positive, downwards mean velocity negative. So he's going upwards when minus 32t plus 16 is positive. And when does that happen?
Wait, so he's falling upwards?
Huh?
Right, when you drop the ball.
He's on a platform. He jumps up and then he falls down. Right? It has to be t's less than a half, right? So, of course we're starting at time is 0, so he's going upwards on this interval of time, right? Between t is between 0 and a half seconds, he's traveling upwards. Similarly, downwards. This implies, t is greater than a half. This minus 32 t plus 16 greater than 0. This would imply t is greater than a half. So downwards. He's traveling between t is a half and 2. Right? Because he stops traveling after 2 seconds. That's when he gets to 1. And we stop measuring his position levels. When is his velocity 0? You already sort of solved for it. It's going to be at a half, right? Plus 0 after a half a second. So essentially what you can see here is what happens is he jumps up. For an instant he stops in the air and then he starts going down, right? That's sort of physically what happens. And probably later on in the semester we'll derive this equation, but I can just tell you now. Right, that's in meters per second.
You got it.
And time per second is, what is it?
I'm not per feet meter.
Minus g over 2t squared plus v0t plus s0, right? Where g is minus 32 feet per second squared, which is the force of gravity. v0 is initial velocity. S0 is initial position. So in our example, he started at 32 feet above ground and his velocity was 16 feet per second at takeoff. Right? And in that, with those statistics, he'll hit the water in 2 seconds. As long as he's only under the force of gravity. we'll stop there. So homework up to 2.3 is due on Thursday.